Bismillahirrahmanirrahim. Dear students, I am Dr. M. Salim Akhtar, Associate Professor of Chemistry. Now, this is our lecture number 40 and it's the last lecture regarding the reaction dynamics chem4146, and we are discussing the relaxation method for the determination of rate constant uh, of our reversible reactions. Now, today we will discuss the relaxation method for second order opposed by second order. That is, today we will discuss relaxation method for second order opposed by second order reaction. Dear students, consider the following reaction in which the reactants A and B and the product C and D exist in equilibrium with initial concentration A, B, C and D respectively. Dear students, consider the following reaction in which the reactants A and B and the product C and D exist in equilibrium with initial concentration A, B, C and D respectively. Equation is A plus B react reversibly forming C plus D with forward rate constant Kf and backward rate constant Kb. That is, A plus B reacts reversibly forming C and D with forward rate constant Kf and backward rate constant Kb. When T is equal to T equilibrium, since the reaction was already in equilibrium, then at T is equal to T equilibrium, concentration of A is A, that of B is B, and concentration of C is small c, and D is of small d. Uh, when the T is equal to T, then the reaction will move in backward direction. Then its concentration will become concentration A will be equal to A plus X, and that of B will be equal to B plus X, and the concentration of C will become C minus X, and that of D, that is equal to D minus X. Now the system moves in backward direction in order to nullify the effect of perturbation, and concentration of A, B, C and D become A plus X, B plus X, not equal but B plus X, and C minus X and D minus X respectively after time t. The rate of forward reaction is given by Rf, that is equal to Kf into concentration of A plus X into concentration B, that is B plus X. that is according to the law of mass action, the forward rate is equal to Kf into concentration of A, that is A plus X, and concentration of B, that is B plus X. This is equation number 1. Once again, consider the following reaction in which the rate of reaction in which the reactants A and B and the products C and D exist in equilibrium with initial concentrations A, B, C and D respectively. Reaction is A plus B, it is reversibly react to form C plus D and with the rate constant, forward rate constant Kf and backward rate constant AB. Now when T is equal to, since the reaction was already in equilibrium, then at T is equal to T equilibrium, concentration of A is equal to A and that of B is equal to B and that of C is equal to C and D is equal to small d. When T is equal to T, the concentration of A becomes A plus X and concentration of B becomes B plus X. The concentration of C becomes C minus X and that of D becomes D minus X. The system moves in backward direction in order to nullify the effect of perturbation, and the concentration of A, B, C, D become A plus X, B plus X, not equal but plus, B plus X, C minus X and D minus X respectively after time t. The rate of forward reaction is given by Rf is equal to Kf into concentration of A into concentration of B, and that is concentration of A is equal to A plus X and concentration of B is equal to B plus X. Then Rf is equal to Kf into A plus X into B plus X. This is equation number 1. Similarly, rate of backward reaction is Rb, that is equal to Kb into C minus X into D minus X. This is equation number 2. Net rate is given by dx of dt, that is the net rate of reaction, that is equal to Rb minus Rf, that is backward rate minus forward rate. This will give you the value of net rate, that is dx over dt, that is equal to Rb minus Rf. Now putting the value of Rf and Rb from equation 1 and 2 in the above equation, we will get dx over dt, that is equal to Kb into concentration of B minus X into concentration D minus X minus Kf into A plus X into B plus X. Now multiplying, we will get KBC into D, C into D minus KBCX minus KBXD plus KBX square minus KF into AB minus KF into BX minus KFX square. That is, we have multiplied these uh, that is b minus x is multiplied as c minus x into d minus x is multiplied with kb, then we will get kb into cd minus kb into cx minus kb xd plus kb x square minus kfab plus kbx minus kfx square. Now dear students, at the stage of equilibrium before perturbation, the rate of forward reaction was equal to that of backward reaction. That is, at the stage of equilibrium before perturbation, the rate of forward reaction was equal to that of rate of backward reaction. This implies as the x is very small, so higher terms can be neglected. Hence, the above equation will become. Now, dear students, once again, the rate of backward reaction is equal to RB, that is equal to KB into C minus X into D minus X. This is equation number 2. The net rate is given by dx over dt, that is equal to RB minus RF. Putting the value of RB and RF from equation 1 and 2 in the above equation, we will get dx over dt, that is equal to kb into c minus x into c minus x. This is topographic mistake. B is written. This is omitted. C minus x into d minus x minus kf into a plus x into b plus x. Now open the brackets and multiplying by kb and kf, we will get kbcd minus kbcx minus kbxd plus kbx square minus kfab minus kfbx minus kfx square. At the stage of equilibrium before perturbation, the rate of forward reaction was equal to that of rate of backward reaction. This implies as the x is very small, so higher terms can be neglected. Hence, the above equation will become dx over dt, that is equal to kb into cd minus kb into cx minus kb into xd minus kb into ax minus kf into bx. This is equation number 3. At the stage of equilibrium before perturbation, the rate of forward reaction at the stage of equilibrium before perturbation, the rate of forward reaction was equal to that of the backward reaction. This implies that Kf into AB, that is equal to Kb into Cd. Putting the value of Kfab in equation 3, we will get dx over dt, that is equal to kb into cd minus kb into cx minus kb into xd minus kb into cd minus kf into ax minus kf into bx. Or this will become dx over dt, that is equal to minus kb cx minus kb xd minus kf ax minus kf bx. KBCD or KBCD, they will cancel out each other. Dx over dt, that will become minus kb into cx minus kb xd minus kf ax or minus kf bx. Now kbx or kfx, they are taken out because they are common. Minus kbx into c plus d minus kfx into a plus b. That is, taking kb and kfx constant in the above equation, we will get dx over dt, that is equal to minus kbx into c plus d minus kf into x into a plus b. Or you can write it dx over dt, that is equal to minus x kb into c plus d plus af into a plus b. Now we can separate the variables and then integrating in this equation, we will get dx, x is taken on the left hand side, that will become dx over x. This will be equal to minus kb into c plus d plus af into a plus b integration of dt. That is integration of dx over x, integration of dx over x, that is equal to minus kb into c plus d plus kf into a plus b into integration of dt. Now the integration of dx over x is equal to log x. Integration of dx over x is equal to log x. That will be equal to minus kb into c plus d plus kf into a plus b into t plus constant. Here dt, integration of dt is equal to t, which will become log x is equal to minus kb into b plus c plus kf into a plus b into t plus constant. Here constant is the constant of integration. This is equation number 5. Now once again, at the stage of equilibrium, before perturbation, the rate of forward reaction was equal to that of backward reaction. This implies that Kf into AB, that will be equal to Kb into Cd. Putting the value of KfAB in equation 3, above equation 3, we will get dx over dt, that will be equal to Kb into Cd minus kb into cx minus kb into xd minus kb into cd minus kf into mx and minus kf into bx. Thus, kb cd plus or kb cd minus, they will cancel each other. Equation will become dx over dt will be equal to minus kb cx minus kb xd minus kf ax minus kf bx. Now, equation, the kbx or kfx, they are common. They can be written out. You can write dx over dt, that is equal to minus kbx into c plus d minus kfx into a plus b, or x minus x, दोनों term में x common है, we will take it out, minus x into kb into constant c plus d plus kf into a plus b. Now separating the variables, x is taken on the left hand side and dt on the right hand side. Then equation will become dx over x, that is equal to minus kb into c plus d plus kf into a plus b into dt. On integration, the equation will become integration of dx over x, that is equal to minus kb into c plus d plus kf into a plus b into integration of dt. Now upon integration, the integration of dx over x is equal to log x, that will be equal to minus kb into b plus d plus kf into a plus b into t plus constant. The integration of dt is equal to t plus integration constant. This is equation number 4. Now, dear students, when t is equal to 0, x will be equal to x naught. Applying this condition to the above equation, we get log x0 is equal to constant. That is, we have calculated the value of integration constant, that is equal to log x0, that is equal to constant. And now dear students, put in the value of constant to equation 4, we will get log x is equal to minus kb c plus d plus kf into a plus d b into t plus log x naught. That is, value of constant is x naught. We have put the value of log as constant, that is log x naught. X naught is taken on the right hand side. If it becomes negative, then equation will become log x minus log x naught, that will equal to minus kb into c plus d plus kf into a plus b into t of using the formula of log a minus log b, that is equal to log a over b. So then this will become log of x over x naught, that is equal to minus kb into c plus d plus kf into a plus b into t. This is equation number 5. This equation is a equation of straight line passing through the origin, where log x over x naught is dependent variable and t is the independent variable. That is, minus kb cd plus kf a plus b is the slope of the plot. Log x over x naught versus t, taking the anti-log on both sides of equation 5. Taking the anti-log of equation 5 on both sides, log of x over x naught will, when we take its anti-log, that will become x over x naught, that is equal to e raised to the power kb plus kb into c plus d plus kf into a plus b into t. X naught is taken on the right hand side. X will be equal to x naught e raised to the power minus kb into c plus d plus kf into a plus b into t. Once again, uh, when t is equal to 0, x is equal to x naught. Applying this condition to the above equation, we get log x naught is equal to constant. We have calculated the value of log constant, that is equal to log x naught. Putting this value of constant in equation 4, we get log x is equal to minus kb c plus d plus kf a plus b into t plus log x naught. X naught is taken on the left hand side. Log of x over x naught is equal to minus kb into c plus d plus kf into a plus b into t. This is equation number 5. Now equation number 5 is the equation of straight line passing through the origin, where log x over x naught is dependent variable, t is the independent variable, and minus kb c plus d into kf a plus b is the slope of the plot log x over x naught versus t. Taking the antilog of equation 5, we will get x over x naught, that is equal to e raised to the power minus kb into c plus d plus kf into a plus b into t, or x is equal to x naught e to the power minus kb into c plus d plus kf into a plus b into t. The above equation shows that value of x, the extent of perturbation decreases exponentially with time. When t is equal to tau, then x will become equal to x naught over e. Hence the above equation will become x naught over e, that is equal to uh, e raised to the power minus kb into c plus d plus kf into a plus b into tau. 1 over e is equal to uh, here x naught is emitted in the right hand side. uh, this is again typographic mistake. Then 1 over e will be x naught and x naught will cancel out each other. That will become 1 over e is equal to e raised to minus kb into c plus d plus kf into a plus b into tau, or e inverse is equal to e minus kb into c plus d plus kb into a plus b into tau, or since bases are same, we can write it as minus 1 is equal to minus kb into c plus d plus kf into a plus b into tau, or 1 over tau is equal to kb into c plus d plus kf into a plus b, or tau inverse is equal to kb into c plus d plus kf into a plus b. This is equation number 6. The above equation is valid only for small perturbations, but in case of the value of rate constant for forward reaction is equal to that of backward reaction, this equation remains valid for large perturbation also. Once again, the above equation shows that the value of x, the extent of perturbation, decreases exponentially with time. When t is equal to tau, then x will become equal to x naught over e. Hence the above equation will become x naught over e is equal to x naught into e की power minus kb into c plus d plus kf into a plus b over tau. 1 over e is equal to x naught will be cancelled with x naught. 1 over e is equal to e to the power minus kb plus cd into kf plus ab into tau. We can write it as e minus 1 is equal to e raised to the power minus kb plus cd or plus kf into a plus b into tau, or minus 1 is equal to minus kb into c plus d plus kf into a plus bo into tau, 1 over tau is equal to kb into c plus d plus kf into a plus b, or we can write it as tau inverse minus 1 is equal to kb cd plus kb into a plus b. This is equation number 6. This the above equation is valid only for small perturbations, but in case of the value of rate constant for forward reaction is equal to the backward reaction, this equation remains valid for a large perturbation. Thank you. Now, dear students, this was our last lecture regarding the reaction dynamics chem 4146. Thank you.